Alrighty, guys, we have made it. We're to the last two topics in college algebra. These two topics are solving systems of equations and systems of inequalities. The good news is these are topics that you've seen in high school, for sure, absolutely. Everyone in this class has seen these topics in high school. You'll remember that when you solve systems of equations in high schools, there's a bunch of methods that you can do, but there's three methods that you really learned in Algebra 2, and you'll learn here again in college algebra. The first being substitution. The second being elimination. And the third being graphing. So let's talk really quick about three of these. We're gonna try and cover all three of these today and sort of get a general idea of how each of these works. First off, if we talk about graphing, you know how to graph a line. We did that in Unit 1 and Unit 2. If you can graph two lines, right, so we have our red line and our purple or blue line here, wherever they intersect, that is the solution to that system of equations, okay? Even when we solve equations by substitution and elimination, that's really what we're finding is we're finding where those two lines intersect. We're finding the intersection point. So that point is going to have two values. It's going to have an x value and a y value. Every solution is an ordered pair, whether or not the question asks for it like that or not. So the question may ask for it as, how many tickets do you have? What is the price, right? It may ask for each of those things separately. But either way, you are getting two values as your solution. Sorry about that. Typically, if you get a solution that is an ordered pair, you're going to put that ordered pair in parentheses, okay? An ordered pair is an XY coordinate, so we will put it in parentheses unless we're asked for it separately as in number of tickets and price, right? Unless it has two separate blanks for each of those. All right, if we want to determine first just if an ordered pair is a solution, what we can do is we can just sub it back into the original equations. So it has to be a solution to both equations to be a solution. If I call this x and y, right? It's in that order, x and y every time. For the first equation, I would have 6 times 1/2 plus -5 equals -2. Notice I subbed in x for x and y for y. Let's check that in the calculator and see if it works. It seems that it does. In the second, we would say 4 times 1/2 minus 3 times -5 equals 17. So what I'm doing is I'm typing the left side in the calculator here. And it does give me 17, which does equal 17, right? And so this point, check, this is a solution. Try the second one, see if it works. If you sub in 0, -2, it seems that that point does work. If you sub in 0, -2 to the second equation, though, it does not work. So it has to work for both to be a solution. In this case, 0, -2 is not a solution to my system of equations because it has to work for both equations, and it only works for the top. It does not work for the bottom. With systems of equations, there are three ways that it can work out. Notice up here, we found one solution, okay? We found one solution. It can work out, because we're talking about graphing, it could work out that you do have one solution, right? You have one spot where those two lines intersect. It could work out where the two lines never intersect and you have no solution. These would be parallel lines. Or it could work out that they're the same exact two lines. You just graph one line on top of the other, in which case you would have infinitely many solutions. There are some vocabulary words that you should note here. If two lines never intersect, then we call that system inconsistent. If two lines always intersect, we call that system dependent, right? We call one line dependent on the other. Take a second and read through these. All right. So now, when we want to solve, first we're going to look at substitution. So we've already looked sort of at graphing here, right? We've already sort of looked at what it looks like to graph. We just graph the two lines and see where they intersect. For substitution, we still have substitution and elimination. For substitution, the idea is, can we get one of the variables by itself very easily? And if you can, then you can substitute into the other equation. So on this one, can I get either variable by itself pretty easily? I think on this equation, if I subtract 4x from both sides, I can get y equals negative 4x plus 5. Notice that I have y by itself relatively easily, right? That's what we're looking for substitution. You sort of get to choose your method when you're doing this. You have to use both equations, so now I'm going to take this other equation, negative 5x minus 4y equals 2. But instead of y, I'm going to sub in what y is equal to. Y is equal to negative 4x plus 5. Now let's try and solve that. Negative 5x minus, that'd be plus 16x minus 20 equals 2. That'd be 11x equals 22, and x equals 2. Remember, when we're solving these, we don't want just one solution, we want two solutions. Or we want a pair, right? We want an ordered pair. We want something that satisfies both x and y. Now that we know x, to find y, what we can do is just substitute again. We substitute once, right? Now we can just substitute again. I know what x is equal to, so I can say y equals negative 4x plus 5. But instead of x, I know what x is equal to. It's equal to 2. So let's finish solving here. Y equals negative 8 plus 5. Y equals negative 3. And so my actual solution here is the pair 2, negative 3. Remember, we're putting it in the order x, y. If you wanted, you could go back to this original set of ordered pairs, right? I'm sorry, this original set of equations, sub in a 2 and a negative 3, 2 for x and negative 3 for y, and make sure that it works. Here's one for you to try by substitution. If you're trying substitution, I'm looking first at the bottom of the equation, right? And I'm seeing that I can get x by itself relatively easily by adding 3y. Now that I know what x is equal to, I can take that top equation and sub it in for x. I know what x is equal to. It's equal to 3y plus 6. All right, solving that equation for y. We get y equals negative 1. Now that we know what y is equal to, we can sub that back into our blue equation up there. X equals 3y plus 6. X equals 3 times negative 1 plus 6. So then x must be 3. And so my actual solution, the ordered pair, will be 3, negative 1. Right, we're subbing x in there. We know what x is equal to. That's solution by substitution. The second is called, they call it addition, but we also call it elimination, right? Addition and elimination. This is our third method. We've seen graphing now, we've seen substitution, now we're going to see elimination. You can read through these steps for a second if you'd like to. What we're going to do though is we're really going to try and get either the x's or the y's to match up. It really helps, I think, to try and get them opposite. Try and get either x coefficients to be opposite or the y coefficients to be opposite. So here, this one is one where I would look at it and I would say, can I solve by substitution? Can I get a variable by itself relatively easily? I could get the x on that top equation by itself, but the problem would be that I would have a bunch of fractions. So instead what I'm going to do is I'm going to get all of my variables lined up. And by lined up, I want my equals to be lined up as well. And I want x's first, y's second, or y's first, x's second, whatever. I want them all to be in the same order. So what I'm going to do, I'm going to rewrite this equation as 5x minus 4y equals 6. And now look, I have everything lined up. The y's, the x's, the regular numbers, the equal sign, everything's lined up just so. Now, can I get the x's or the y's to be exactly the opposite of each other? So what I'm going to do, I'm looking at the x's, okay? And if I can multiply those to get them to be the same but opposite, then I'll have something that will eliminate. So what I'm going to do is take this whole equation and multiply it by 3. Take this whole equation and multiply it by 5. And that should give me 15x and 15x, right? You see what I'm saying? That would be 15x minus 12y equals 18. I just multiplied everything here by 3. Now I'll multiply everything here by 5, and I have negative 15x plus 35y equals 5. Notice now that the x's are the same but opposite, and so now if I add these two equations together, I'll end up with no x's, right? I'll end up with 0. And then 35 minus 12, or negative 12 plus 35, either way you want to look at it, is 23x. I'm sorry, that's a y, 23y. 18 plus 5 is 23. I can divide both sides by 23 and get y equals 1. Again, I want an ordered pair. I can go back to any equation throughout the whole process and try and find x. I'm just going to go back to the one that looks easiest. I'm going to take this one. So 5x equals 4y plus 6. But I know that y is equal to 1. So then 5x equals 4 plus 6. 5x equals 10. Divide by 5, x equals 2. And so my ordered pair, my solution is 2, 1. That's how elimination works. We try and get either the x's, you can get the x's or the y's. I could have multiplied to try and get the y's to be the opposite. You just got to get one to match up, either the x's to match up or the y's to match up. You really want it to be the opposite so that when you add, they will cancel out. Try this one. I've already taken the equations and set them up so that everything is just so in order. The x's first, the y's, the equals, the numbers. So step 1, see what we're going to multiply by. I think if I multiply the first equation by 2 and the second equation by 9, that will make the y's match up. The reason I chose the y's here is because they already have the opposite sign. You see that? One has a plus and one has a minus. So back here, I could have chosen either. They already had opposite signs. In the equation that I have, I could have gotten the x's to match up by multiplying one by negative 3 and the second equation by positive 2, or vice versa. But here, I just think it's easier to get the y's to match up. Oh man, I just uncovered the wrong part of my equation here. All right, once you get them to match up, let's try and multiply them. So that makes 4x minus 18y, 27x plus 18y. Notice the y's are the same but opposite, so that when I add, I'll only have x's left. Divide by 31, you get x equals 5. Since I know x, I can go back to any equation and sub x back in. I just went back to this equation and subbed x back in and solve and get y equals 1. Even if you multiplied by a different thing, or if you solve by substitution, or if you solve by graphing, any method of solution is going to get you the same exact solution. So my point is 5, 1. Here's another. Solve using elimination. This one has fractions. So the first thing to do would be to try and, I would say, eliminate the fractions and get your x's and y's in all your ducks in a row. Get everything in order. So to do that, I multiplied the top equation by 10, right? And then I distributed on the bottom equation. Our y's are still out of whack, right? There's y's on the left, y's on the right, all over the place. So now, if I move the y's over, this is what it looks like. I can multiply by these things to try and get the y's to match up. Again, I chose the y's because they're opposite sign already. One of them's a plus and one of them's a minus. Multiply by 12 on top and 10 on bottom gives me a 120y and a negative 120y. That's what I wanted. I wanted opposite things there. That way when you add them, there's only x's left, and then you could divide to get x. Not a nice number, but it is an answer. Now I can take that x and sub it into any equation that I want to up there. We're going to try and choose the easiest one. Sub in x, divide by negative 1, and you get your solution. Again, this does need to be an ordered pair, and so my solution is negative 1.857, comma, negative 2.643. Now that we've seen all three, we can sort of pick and choose which method we want to choose anywhere. This just says solve the system. It doesn't say how. You can pick whether you want to solve it by substitution or elimination. What would you want to do? I chose elimination. I prefer elimination when I can use it, because it seems to work out a little bit quicker. If I multiply the whole top equation by -3, my y's already match up. I can add those equations together. Oh no, look what happens. Everything eliminates, and we end up with 0 equals -6, which is not true. This is one of those equations that's inconsistent, right? We get an inconsistent answer. This does not work, never. It never works, and so we have no solution. These two lines, if we went to graph them, we would end up with two lines that are parallel, right? They would never intersect. All right, how about this one? We've already got one of the equations solved for y, so I would say we'd use substitution here, right? In our second equation, we can substitute in what y is equal to. This is what y is equal to in the first equation. Try and solve for x, and look what happens. We get something that's just absolutely true. It's not ever not true. In the last one, we got 0 equals -6. That is not true. This is a true statement, though. And so what that means is no matter what I sub in for x, I'm going to have a correct answer. So all real numbers are my solution. Any number for x and any number for y. Any number for, well, I shouldn't say all real numbers. That's a bad way to say this. I should say that there are infinite solutions, right? There are infinite solutions. They're all on this line. You know, both of these lines are actually the same. Y equals 2x minus 1. So it looks something like this, right? And if I was to graph the second line, it would just land right on top of that line. Any point on that line is a solution. So this one, there are infinitely many solutions. Applications, all right, so applications that involve more than one variable are ones where we could solve by substitution, elimination, graphing, however we choose. A hospital uses a 15% bleach solution to disinfect a quarantine area. How much 6% bleach solution must be mixed with an 18% bleach solution to make 50 liters of a 15% bleach solution? So we have different things going on here. Typically, you want to group your equations. We want to make two equations, obviously, right? Because we're solving systems of equations. That's the whole unit. We're solving systems of equations, first off. But second off, there are different things at hand here. We have percentages, and then we have volumes, right? A liter is a volume. We don't know how that relates to the percentages. So I'm going to try and group things together here. Percentages and volume. That's how I'm going to make my two equations. So as far as percentages go, if I call my 6% bleach solution my x solution and my 18% bleach solution my y solution, I could say that's 0.06x plus 0.18y equals 0.15. Percent plus percent equals percent, right? I'm keeping all my percents in one equation. Now, if I take all of my x solution and add it up to all of my y solution, I'm going to get 50 liters. And again, here I can solve by either substitution or elimination. I tend to prefer elimination when I can do it. So what I'm going to do is I'm going to multiply this whole equation by 100 to try and get rid of the decimals, and that's going to give me 6x plus 18y equals 15. Then to get this one to match it, I'm going to multiply this whole equation by -6. So I get -6x minus 6y equals -300. I can add those two equations together now. 18 minus 6 is 12. 15 minus 300 is -285. 12y, -285. Something's not checking out here. And I get -23. 75. All right, this is not working out. We're going to have to go back and rethink our equations up here. So what I'm doing, this process that I'm doing, is I'm thinking we're adding together volumes of solution to make 50. There's no way one of those volumes is -23, maybe +23, but obviously I have something incorrect here. How much 6% bleach solution must be mixed with an 18% bleach solution to make a 15% bleach solution? I don't like this equation. I'm not sure exactly what's wrong with it. I'm going to have to think about it for a minute. Here's what we'll do. Let's move on to this last example here. I'll give you a second to write down the example. You can work it, and then we'll come back to this one. Here's what I'm thinking here. I'm thinking this is not just 0.15. I'm thinking this is actually 0.15. It's a percent of a solution, right? And right now we just have it as a number. It's not as a percent of a solution. It's not as a percent of a thing or a percent of a total. And so what we need to do probably, let's go back and see if this works. See, this is how math works, is you're just sort of doing trial and error until it works. 0.06x plus 0.18y equals 0.15, and this is of my total, right? This is of my x, 6% of my x plus 18% of my y equals 15% of my total, x plus y. I think this is going to work out for us now. Now this may take us a little bit extra to solve, and I may actually choose to do eliminate or substitution now. Let's just see what happens. I'm going to take this equation and play with it for a minute and see if I can get my ducks in a row here. So that'd be 0.06x plus 0.18y equals 0.15x plus 0.15y. If I move everything over to the left side of the equation, 6 minus 15 is negative 0.09x plus 0.03y equals 0. All right, let's try this out. I'm just going to rewrite my percent equation here, okay? Now that I've messed with it, is negative 0.09x plus 0.03y equals 0. All right, again, I'm going to multiply this whole equation by 100. So then that would give me 9x plus 3y equals 0. To get one of my variables to match up, I'm going to multiply this equation by negative 3. So that'd be negative 3x plus 3y equals negative 150. Now when I add my two equations up, I get 6x equals negative 150. No! Oh, it's plus 3y. Negative 3x. Did I multiply by positive 3? Okay, that's why. If I multiply by negative 3, that would be negative 3x minus 3y equals negative 150. Yeah, 6x equals negative 150. Oh, man. X equals negative 25. All right, well, here we go. I've made another mistake. What I'm probably going to have to do is cut this video and come back and rework example 7 at a different time. I don't know what I'm doing wrong here. I'm going to have to piddle around with this a little bit. 6% bleach solution must be mixed with an 18% bleach solution to make a 15% total. And we add up to a total of 50 liters. Negative 0.09 plus 0.03. Oh, man. I see it now. When I multiplied this equation here, let's just go back a step. When I multiplied this equation right here by 100, I didn't keep my negative sign. You see that negative sign right there? That's where I messed up. I didn't keep my negative sign. I knew I'd set this up correctly. All right, now with that, now that x is negative, why don't we multiply this whole equation by 9, right? And so then our x's will be opposite. 9x plus 9y equals 9 times 50 would be 450. That adds to 12y equals 450. The x's eliminate, so our elimination is working. 450 divided by 12 gives me y equals 37.5. All right, now we're working. Then I can use this equation right here. Since x plus y equals 50, and I know y, that means x plus 37.5 equals 50. And so 50 minus 37.5 gives me x equals 12.5. So then my solutions here, since x is my 6% bleach solution, my problem would be worded how much 6% bleach solution. And then in that blank I would write 12.5 liters. How much 8% bleach solution? And then in that blank I would write 37.5 liters. All right, I'm sorry for the confusion, but I'm glad you got to see the process of math at work here, right? So this is the process. You work, you realize something isn't working, right? So every time I got a negative number, I kept realizing there's got to be something incorrect because I'm trying to add up to a positive 50 liters. I can't have a negative amount of liters. So I had to go back and rework and refactor my problem. All right, let's try another. A riverboat's traveling upstream against the current on the Mississippi River. It takes 3 hours to travel 24 miles. The return trip takes 2 hours. Notice that he's doing the same 24 miles, right? So the distance is going to be 24 miles every single time. This is distance, and we're going to use this D equals RT, distance equals rate times time formula. All right, when traveling upstream, I'm just trying to put together this distance equals rate times time, right? So distance equals 24. The rate going upstream, right? The rate going upstream, he's going to be going slower upstream. Is going to be how fast he's going minus the river. It's his boat speed minus the river speed, minus the water speed. And the time is 3. It says it takes him 3 hours upstream. All right, downstream, the same process. We know our distance is 24. Our speed is going to be our speed, R, rate, R, plus the water, right? He's going faster. And it says it takes him 2 hours. That's our time. I can, again, like I've been saying, try to get my ducks in a row and get the R's and the W's to sort of make sense on the right side, get those to match up. 2R plus 2W. And then I can either do substitution or elimination. It doesn't matter which you choose. I just wrote those two in opposite order so that it looked like the prior problems. But this looks like a problem that we can solve with elimination. We can multiply both equations by the top equation by 2 and the bottom equation by 3. Then the W should eliminate if we add those two together. Completing this problem, we get R equals 10. If we get R equals 10, it says it's going to have two blanks again, right? It's going to say how fast is the speed of the boat. We called that R, right? R for rate. The speed of the boat is 10 miles per hour. Then find the speed of the current. I have a W for water, the speed of the water. To find the water, we just need to go and sub in our R to either of those equations. I chose the bottom equation, 2R plus 2W. And we end up with W equals 2. So the speed of the water is 2 miles per hour. Again, it's going to have a blank. It's going to have two blanks. One for the speed of the boat, one for the speed of the water. All right, thank you guys for bearing through example 7 with me. I know that was a toughie, but again, I'm glad you got to see that process, and I hope you understood example 8. The word problems are absolutely the hardest part. If you can solve systems of equations by substitution and elimination, that's the most important part, but there will be an application question that's asked of you for sure.